About linear functions. So most of your linear functions will be in the form of y. That's your f of x equals 5x minus 4. All right, so the slope is 5. Your y-intercept is negative 4. We can plot the y-intercept. We can count up 5 and to the right 1, plot our points, draw your line. All right, so that's graphed. Remember, what is the average rate of change again? That is the same as slope. So if they throw this out in a word problem, you know that it's the slope. Determine whether the linear graph is increasing, decreasing, or constant. Well, from left to right, it's going uphill, so it's increasing. Now, what you're going to be asked to do is to take a set of data points. They'll give you a table, and they're going to ask you, does this table determine a linear function? Well, think back to your graph. Your y and your x's have to increase at the same rate. So what we're going to do is look at the rate of increase on your x's. So from negative 2 to negative 1, I increased by 1. From negative 1 to 0, 1. 0 to 1, 1. 1 to 2, 1. They're all increasing at the same rate. If I'm at 4 to 1, then 1 to negative 2, to negative 2 to negative 5 to 8, or negative 8, they're all decreasing by 3. So in between each of these changes here, this is your change in y over your change in x, which means they're all the same values. That means it's our slope. You have a linear function. Now, we call this technique the difference test. It's called the first level because on the first time you found the difference of your data points, your x's and your y change were the same. So we have your slope of negative 3. You have this point right here, 0, negative 2. Anytime your x is a 0, that's your y-intercept, so that's negative 2. There's your function. Now, be careful because don't be fooled. If for some reason, let's say they had another number down here. This x was a 4, and this was negative 14, and that goes from plus 2, and that's a negative 6. And don't go, well, the numbers changed. Well, remember, it's negative 3 over 1, negative 3 over 1. Down here would be negative 6 over 2, which reduces to negative 3 over 1. That's still okay. If we check our next table, notice the x's are the same, so those are all plus 1. Then we'll go look at the y column. Negative 4 to 0 is an increase by 4. 0 to 4 is 4. But 4 to 9 is an increase of 5. 9 to 13 is 4. As soon as you're different, this is not a linear function. Okay? And righty then. Next, you're going to start comparing functions with equations and inequalities. So let's say, for example, 3x plus 5 is your f of x, and g of x is negative 2x plus 15. If they want you to solve for f of x equals 0, that means put 3x plus 5 in for f of x, set it equal to 0, and solve for x. X equals negative 5/3. If they change the equal sign to a greater than symbol, you can just put the greater than symbol in for the equal symbol as long as the following condition is true. As long as you did not multiply or divide by a negative number in your work. So we always want to make sure that your x terms are positive because then you're not dividing or possibly multiplying by a negative number to the other side. So keep that in mind when you do the work here for your linear functions. Keep those x terms positive. If they ask us to solve for f of x equals g of x, that means Set the two function expressions equal to each other. 3x plus 5 equals negative 2x plus 15. Again, keep your x terms positive. So I'm going to take this negative 2x and I'm going to add it over to the left. And since we're solving for x, I'm going to get rid of the plus 5 by subtracting it over. I'm going to do those two steps at once. So that gives me 5x is equal to 10 divided by 5, x is equal to 2. Again, if they want to make it an inequality, as long as these are in the same order, you can put in the greater than or equal sign for the equal sign. And also, as long as you didn't divide by a negative 5, it was a positive 5, it's okay. If they put g of x first and f of x second, then flip everything around to match the order in which you set up this problem, and then you can just drop in your inequality symbol. Okay? All right, so we have our interval notations or your inequalities. So in essence, for the word problem, this first part was really finding an x-intercept. This was looking for all positive y coordinates of the function. Remember, f of x is the y, so where are all the y coordinates greater than 0? Setting two functions equal together finds out where the two graphs will intersect. They intersect at the x value of 2. And down here with the inequality symbol, that just means we're looking for all the y coordinates of the f function to be bigger than the y coordinates of the g function. Now, another thing I want to show you here real quick is we're going to go to graph this. Let's go graph these two functions, red for f of x, blue for g of x. And I want to just plot these points and make the graphs. So problems that you're going to see in the near future, that we want to use the graphs to possibly solve these inequalities just to make sure they're right. So if we graph this, y-intercept of 5, slope up 3, right 1, straight line draws your graph. Y-intercept of 15, down 2, right 1, down 2, right 1. There's that intersection at x equals 2. And I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if you take the 2 and you plug it into either one of these two functions, you should get a y coordinate of 11. 3 times 2 is 6 plus 5, 11. Negative 2 times 2 is negative 4 plus 15, 11. So if you think back, let me go back here real quick. Where is f of x greater than g of x? If you think about the graph, f of x is in red, g of x is in blue. Where is the red graph higher than the blue graph? And that is at x is greater than 2. Or in this case, we had greater than or equal to. X is greater than or equal to 2. So when you're working with linear functions, you can make some quick graphs, and they don't have to be perfect. You just need to be able to algebraically find the exit where they intersect. Anybody can plot a y-intercept, positive or negative, and draw a slope that's positive uphill, negative downhill. Okay? So keep that in mind when we look at this next problem here. The author wanted to incorporate a little economics here. Quantity supplied of a good is the amount of product that a company is willing to make available for sale at a certain price. Okay, so anything that talks about supplied is a company. Anything that talks about demand is us, the consumers. Quantity demanded of a good is the amount of product that us consumers are willing to purchase at that given price. So what do the two try to do? They try to come up with an equilibrium price. This is where you set these two functions to get equal to each other to find a price that both the consumer and the company are willing to sell the product for. So equilibrium price of a product is defined as the price at which both quantity supplied is equal to quantity demanded. Equilibrium quantity, this is defined as the amount of demand or supplied at that equilibrium price. So once you find equilibrium price, you can find equilibrium quantity. So let's look at an example. Let's suppose that the quantity supplied, capital S, and the quantity demanded, D, of gaucho dogs at a football game is given by the following function. S of P is equal to negative 20 plus 30P. D of P is equal to 100 minus 10P, where P is the price of our gaucho dog. Find the equilibrium price for the gaucho dogs at the football game. What is the equilibrium quantity? So equilibrium price means set these two functions equal to each other. S of P is equal to D of P. Okay, we can do that. This is finding out where the graphs cross. Again, work with positive variables. So negative 10P on the right, I'm adding that over to the left. I'm going to get rid of the constant negative 20, add that to the right. 40P equals 120, P equals 3. My equilibrium price is $3. My equilibrium quantity means just plug the 3 into either function. It doesn't matter. You should get the same thing. So I went to S function, put in the 3, negative 20 plus 30 times 3, which is 90. Negative 20 plus 90 is 70. So we need to sell, we'll be selling 70 gaucho dogs. That's how much I have to have ready for the game. Now, let's say they ask us this question. Determine the prices for which quantity demanded is less than quantity supplied. All right, the consumer's demand is less than the company's supplied. Okay, so that's going to be D of P is less than S of P. Oh no, remember before in the previous example we could just throw in the inequality symbol if you wanted to, if they were in the same order. They're not. So you can either flip this or just make a quick graph. If I make S of P red, it has a negative y-intercept, so somewhere down here with a positive slope, so that goes uphill. My other equation has a positive y-intercept somewhere up here with a negative slope. It goes down. They're going to cross, and I know they cross when P is equal to 3. All right, so S of P is in red. So I'm going to change that blue font to red. When is the blue graph's y-coordinates less than the red graph's y-coordinates? That's everything to the right of that intersection point when P was equal to 3. So when P is greater than 3, those are my answers. That's when the price of the gaucho dog is way too much, which means the price goes up, the demand goes down, and your gaucho dog supply is going to be, you're going to have too many left over. So again, like we said, if we were to switch the S of P and the DP around, which makes that S of P greater than D of P, you got your straight substitution there. What do you think will eventually happen to the price of the gaucho dog if the quantity demanded, if the consumer's demand is greater than the quantity supplied? Well, when the consumer's demand goes up and the supply goes down, that means the price has to go up. Okay, next linear function example. In 2002, Major League Baseball signed a labor agreement with the players. In this agreement, any team whose payroll exceeded $136.5 million in 2006 had to pay a luxury tax of 40% on the salary that exceeds $136.5 million. Write the linear function that describes the luxury tax, capital T, of a team whose payroll was P. So T of P equals 40% as a decimal multiplied to whatever goes over the cap. All right, this prevents teams from spending more money than they can take in. So the domain for this particular function has a restriction. You can't apply the tax unless the team's payroll, P, goes over 136.5 million. So we can write it as an inequality or write it in interval notation. So what was the tax of the New York Yankees, whose 2006 payroll was 171.1 million? They definitely exceeded the cap. So we put in 171.1 in for P. We subtract the salary cap. That's 34.6. We multiply it by 0.40, and we get 13.84. That's millions of dollars, which the league calls a tax. The New York Yankees had to pay $13.84 million to the league because their payroll went over. So that means, in theory then, their overall payroll with the tax, holy cromoles, was 184.94, almost 185 million. You had to pay an extra 13.84 million. I don't know about you, but I think I would have trimmed back on the payroll. You can also ask this question: what is the payroll of a team who had to pay a luxury tax of 11.7 million? So 11.7 million goes over here where the tax was at, the T of P. So that's the tax paid. And now solve this for P. So get rid of the 0.4 being multiplied on the outside of the parentheses, so we divide that over. You could distribute it if you wanted, but you can then do more work. So I'm going to keep this as short as possible. So my calculator told me 11.7 divided by 0.4 is 29.25. Parentheses are gone. Add over the 136.5. This payroll, was 165.75 million. And that's 4.1 with its linear functions.